Okay, I want to look at closed systems, but this time I want to look at condensing steam. So let's take closed systems. And we're going to condense steam in a tank or in a piston cylinder arrangement. So let's take this situation where we have a piston cylinder arrangement, and we'll take two instances of this. One where we have stops so that it acts as a tank, and the other where we take away the stops. So let's do the first. Let's remove the stops first and look at the situation where we remove the stops and the piston can go down. Of course, you know, when piston is going down, work is being done on it. Work in, recall, is the opposite of work out, so that's minus the integral of P dV. And I want to start with 1 pound mass of saturated vapor, steam, at 212 degrees. You know that since it's 212 degrees, it must be, and it's saturated, it must be at P equals 14.7 psi. So let's suppose that this piston can go down some. And what I want to do is I want to remove 500 BTUs from 1 pound mass of steam. So our energy balance is in equals out plus accumulated. And the accumulated is mass times U2 minus U1. And the out is the heat that we're removing. Let's put it Q out. We'll make that 500 BTUs. The work in is equal to minus the integral of P dV, so minus, and notice that if this is steam condensing, and we set we'll make this a weightless piston, so that the only pressure is the pressure of the atmosphere. We'll make that 14.7. Then the pressure doesn't change, temperature doesn't change if it's condensing and stays saturated. Since the pressure doesn't change, the temperature won't change. And so what we have is a little bit of liquid condensing down in the bottom here. And then the piston will go down, so that would be the PdV, or mass, times the integral of P dV, where that's a small v. Lowercase v to indicate specific volume, or minus 1 pound mass, times little v2 minus little v1 equals 500 plus m, which is 1 pound, times U2 minus U1. Okay, it was a saturated vapor at state 1, so it's easy to find these properties. V1 is the specific volume of a saturated vapor, 26.805. Let's just say 26.8 is V1. U1 for steam at saturated vapor conditions at 14.7 psi is 1077.4 BTUs. So that sets up the problem. Actually, what I'm missing here is P. To put in P is 14.7 psi. So if we move down a little bit, we'll copy this down. We have 14.7 times V2 minus 26.8. Now I'm going to have to multiply that. Recall that's going to be psi feet cubed. And this is times our 1 pound mass. So this will be psi feet cubed times 0.185 BTUs per psi feet cubed is equal to 500 plus M times U2 minus 1077.4. Okay, so this is what we have so far. Now I've made a little table here to show us our results, or our summary of our information that we've compiled on this problem. We have T is 212, P is 14.7, the quality is 1 because it started as a saturated vapor, the volume is 26.8, and the internal energy 1077.4. Now at state 2, what do we know? Well, we know that it's probably going to condense, so with the constant pressure of 14.7, then the temperature will now be, again, 212, assuming that it hasn't completely condensed. And that's an assumption that we'll verify later. Now we know that, supposing that it is a mixture, that at state 2, U2 is equal to 1 minus x times UF, and UF is 180.1, plus x, and this x2 I should say, x2 times UG, which is 1077.4. That introduces a new unknown to the problem, x2. So we don't know what x2 is. And let's write, so far let's count our equations and unknowns so that we can specify this problem. We have, first of all, our energy balance here. This gives us one equation. And let's see, I'm going to write these out in orange. One equation and two unknowns. I'm going to write down what my two unknowns are. My unknowns are V2 and U2. Okay, I have another equation here. U2 equals a function of x2. So that's two equations. I'll write my equations in Roman numerals. And my unknowns, cumulative unknowns, I have 3 now because I've added a new one. And I'll write down that new one is x2. So now I have 2 equations and 3 unknowns. And finally I'm going to write out equation 3. And this will be V2 is equal to 1 minus x2 times VF, and VF very small for the liquid, 0.01671, plus x2 times the G, which we found earlier was 26.8. So we have 3 equations, and now we have 3 unknowns. So we have what we call described this problem. So I'm going to write described, meaning that all we have to do is solve these equations simultaneously for our missing variables, and we'll solve the problem. That's a powerful technique. If we have 3 equations and 3 unknowns, we know that we can solve it. So, see, let me go back up and correct this. There should be a minus here. Minus 14.7 times V2 minus 26.8 times 0.185. And we'll plug in our second 2 equations into equation 1, and we finally find an equation that looks like, write it out again. So if we write this all out and plug it into our equations, plug in equations 2 and 3 into equation 1 and solve for x2, we find that x2 is equal to 0.484, or that tells you a little over half of the liquid has condensed in the process. Now, if we look at the other case where the tank volume stayed constant, let's go back up and look at our figure. Suppose the stops remained in place, and we'll call this case 2. Well, state 1 would be the same, but now we have stops in place that keep this piston from going down. So what's the result there? How much work is done from that? Work equals the integral of P dV. So dV would be 0, as we would have with a rigid tank. No volume change, no work done. And so V, we'll call it V3, would be equal to V1. So we'll go down and look at our table again, and we'll add in a new entry. We'll call it state 3. State 3, the temperature, we don't know. We removed 500 BTUs of heat. Say we remove the same 500 BTUs of heat, but we don't know what the temperature is. We don't know what the pressure is, and we don't know what the quality is. We still know we're going to assume that some of the vapor condenses, so this equation U2 will still apply, except this equation will apply, except we'll call it U3. So we'll make that U3, X3, that equation will apply. Our energy balance will change, so our energy balance will now be 0 work equals 500 plus U3 minus U1, which is 1077.4. So equation 1 looks a little different. There's one equation and one unknown, U3. So we'll solve for U3 from this equation and find that U3 is equal to 500 minus 500 plus 1077.4, or U3 is equal to 577.4. Now this seems to be a little easier to solve, but you'll see in a minute it's not quite true. We know that V3 is the same as V2 because the volume did not change. So V3 is 26.8. And we know that U3 is equal to 577.4. Now if we assume that it's saturated at that point, all we need to do is find the quality that gives us saturation, but we really don't know what the pressure is here. We need to find the quality that gives us a U of 577.4, but we don't know what the temperature is. So this becomes actually a trial and error problem, and let me mark it out below. The problem becomes one of knowing two properties, find the third. We have V is equal to 26.8, and we have U is equal to 577.4. Two properties, find the third, and that is actually a fairly difficult problem to solve. So by trial and error, we would say, first of all, that V3 is 26.8 equals 1 minus x3 Vf plus x3 Vg, and U3 equals 577.4 equals 1 minus x3 Uf plus x3 Ug. All we have to do is find the pressure or the temperature that solves this problem. So if I could sketch this out, we'd have a trial and error solution. Guess P. Find values for Vf, Vg, Uf, Ug. And when you are done, does this V equal 26.8? Does this U equal 577.4? If that's true, then you've guessed the right P. If it's not, then you go up. Let's put yes. Done. No. You guessed a new P. So basically that's a trial and error solution. Complicated to do, but the physics of the problem is fairly easy to understand. So I'll leave that one for homework. And the answer is, so with a little work, you find that P3 is approximately equal to 6.7 psi, and X3 is approximately equal to 47%. So let's say 47% X3, which means about 53% of the vapor condensed in that process. That's an interesting process because with 6.7 psi, that means the atmosphere is doing 14.7 minus 6.7, bearing down on the container that holds that vapor. And so you can see on the internet, and I'll have one on my channel, some videos where you can take the heat out of a condensing vapor. All you have to do is get it to boiling, take the heat out of condensing vapor, and you have a net. In this case, if you took 500 BTUs out, you would have a pressure down in that tank of 6.7. The tank would collapse. So that was an interesting experiment I saw in 4th grade and never forgot it. The pressure of the atmosphere is really quite a bit more than you think it is. When you drop the pressure inside to 6.7, you can wind up collapsing the tank. So this is a nice review of two situations. One where you take the piston and let it slide down at constant pressure, and the other where you hold the tank and then let the pressure drop as the vapor condenses. A couple of more examples of closed systems and the energy analysis on these systems.